So the title of the presentation, that doesn't necessarily mean the content of the presentation, is OpenSSL providers in Rust for the PQC transition. And it's supposed to be a workshop, and I am losing the microphone, yes. Okay, but let's start from who am I? So I'm a member of the academics community, first of all, and I want to use this opportunity of being on stage and speaking to all of you and holding a microphone and nobody can stop me, for invite all the academics and everyone else to join the community hub at openssl-communities.org, join the communities you self-identify with, start discussions. There are no silly questions, there is no useless feedback, everything is welcome, and that's the only way that we can move OpenSSL forward and make it so that it actually meets the needs of all its users. So please join me there. In terms of my contribution to OpenSSL, as Paul mentioned, I've been contributing to OpenSSL for many years as an external contributor, then committer, OTC member, SRT volunteer, all kind of things. But the reason I'm saying this is I started small. It was almost an accident. And I'm still here. It's fun. So I really encourage you. Start whatever you are doing with OpenSSL, we want to hear about you. So please join the OpenSSL Communities Hub. And if you want to reach to me personally, you can see at that URL all the information that you never wanted to know. Now I'm changing my hat. Now I am the researcher, Nicola Tuveri, the serious one. And I've been focusing my research on mainly two topics. So we have heard the whole day about microarchitectural side channel attacks, but we are not going to talk about that today. The other focus of my research is bridging the gap between the bleeding edge, state-of-the-art, all the buzzwords, cryptographic implementations, and mainstream adoption. And on this last topic, I've been boring the reviewers for years about first engines, now providers, to bridge these gaps. You can see here a list of papers if you really want to get bored reading about this. But today, we are going to talk about Aurora, which is the last instantiation of these boring the reviewers with this stuff. So what is the QUBIP project? They are funding my presence here, so I have to do the regular advertisement. It's a European Horizon Europe project, and we are now in its last year, and it involves 11 partners all over Europe. You can see here the countries, there's Spain, Italy, Czech Republic, and Finland. And we are now in the last year, as I was saying, and this is the time where all the things that we promised we will do are actually coming to fruition. And if you attended the demo from my student Akif and Francesco yesterday, you saw all the fun parts. Now I'm going to cover the boring ones. In QUBIP, we insisted a lot on the methodology, and the idea here is that we are very interested in the cryptographic agility. In this case for PQC, but more in general, we want to make sure that applications that are built on top of crypto libraries like OpenSSL, NSS, that have mechanisms to plug in cryptography externally can leverage this capability to actually have way more freedom than they used to select not only which algorithms they want to support, but also if they, for whatever reason, disagree with the choice of the library of their choice of which implementation for the specific algorithm, they can plug in their own choice of cryptographic implementation for the algorithms they care about. So we are doing this in the case of OpenSSL through providers. Providers can be loadable modules, can be statically compiled. For the purposes of this presentation, I will only talk of providers as if they were loadable modules. This doesn't limit the scope of what we can do with providers. So the demo yesterday of Akif and Francesco, you will see at that link the recordings and the slides at some point after the conference, and you can see this thing actually in action. And the reason why I'm repeating this slide that was also available in what they showed yesterday is that among the various things where we are applying this QUBIP methodology, we have we at Tampere are responsible for internet browsing pilot demonstrators. So we lead this task in cooperation with Red Hat and our partners in Italy and Spain. And the whole idea here is to demonstrate how we can use the QUBIP methodology that I mentioned before to achieve a full end-to-end PQC TLS 1.3 connection between client and server in a way that is completely transparent for the users. So for the users, the user-facing aspect is Firefox in our selection. And we work to modify NSS and provide an external soft token that implements cryptography so that Firefox, that already provides support for hybrid PQC key exchange, also is augmented with support for PQC authentication, both in the pure and composite versions. And on the server side, we based our server stack on OpenSSL, and we pick NGINX, but any other web server working on top of OpenSSL, as long as they use the modern interfaces, will get the same kind of agility without compromising on the reusability, to plug in an external provider that we dubbed Aurora, which is the one that actually provides OpenSSL with the PQC implementations. And one peculiar thing about Aurora is that we call these shallow loadable modules, and the idea is that we do not select. We heard from the OQS provider and Michael's presentation, one of the anti-goals was we do not want to select a winner in terms of algorithms. And we went one step forward and we said that not only we don't want to select a winner algorithm, we don't want to select a winner implementation. So the idea is we want to facilitate experimenters to try out different implementation, not just different algorithms. And that's probably in a nutshell, the main difference between Aurora and OQS provider, if you are wondering. The other very big difference is that OQS provider, despite being a research project, is way more mature than Aurora. So you will see a lot of, we shouldn't leak these comments in the code that you will see. Don't be scared, it's Rust, but don't tell anyone, it's all unsafe all the way down. And please don't trigger Bob. Yeah, sure. But you might be wondering, okay, didn't you promise a workshop? What about Rust? Where is all this stuff? Well, let me start. Let's see what I have there. Yes. Let's start from discussing what a provider is. If you ever wonder what a provider is, and after 3 days of OpenSSL conference, you still don't know, shame on you. No. So the resources to find more about providers are the man pages. They are not the friendliest resource of documentation for someone that is not already familiar with provider, which is like a chicken and egg problem. But in a nutshell, a provider, in OpenSSL terms, citing the documentation, is a unit of code that provides one or more implementations for various operations, for diverse algorithms that one might want to perform, which is very vague on purpose. It kind of wants to say that the provider can do anything you ever wanted, but we couldn't say it that way. When you actually open that man page, you notice at the end the C also, and there is like a list like this long about, well, there is Crypto 7, there is provider base, provider digest, provider anything. So it's a tricky part of the documentation. You also see that I was very timely in preparing the slides, and so I have a to-do AI prompt to show all this convoluted graph. Use your imagination. You are the AI today. And what is important for this presentation is that we will cover mostly what provider base actually documents, which is the way that the provider gets to interact with the fundamentals in the OpenSSL core and vice versa. If you want a more serious introduction to providers, if you didn't know, OpenSSL has a YouTube channel, and there's very good seminars by Matt, Tomasz, Richard, that actually went into the details of why providers, how they are used in practice, for what purposes you might be interested in using providers, and Richard had a very good seminar about how to write a provider skeleton. And most of the things that you will see next are actually stolen from that webinar. So what does a provider look like in C, because OpenSSL is a C project? These actually, I stole all these from Richard's presentation. Only the typos are mine. But everything that works is thanks to Richard. But at the very minimum, an OpenSSL provider is a blob, a binary blob that exposes one single function, which is usually called OSSL provider init, and it can be loaded dynamically at runtime. OpenSSL core will find the OpenSSL provider init symbol, will call that thing, and after that, the provider gets to do all its magic. So this version of the provider, by the way, you can find at that URL the source of this very useful provider, is just saying hello world, because we are programmers and that's where we start. So let's try to see if these actually, and it's not doing anything else, it's just setting the output of these OSSL dispatch table to an empty list that just as an end guard. Let's see if the demo actually works. So we are in the nonsense folder where there's only the hello world.c file, and I can demonstrate, because it's a security conference, there's a proof here that this is what was in the slide before. And if I just do make clean, because who knows what is the state right now, I compile it with Clang so that it is position-independent code. I then link it so that the OSSL provider init function symbol is actually exposed. And then I loaded OpenSSL list provider hello world to load the provider. And I ask list to list the providers in a verbose mode. And whole and behold, our provider has been loaded. It prints the hello world message. And OpenSSL tells us that among all the providers, there is one that is being loaded, and it's called hello world. And then it tells us, warning, unable to query provider parameters for hello world. And the reason for that is that we basically passed an empty list of functions. So this provider, from the OpenSSL core perspective, does exactly nothing. But wait, I promised you to give you how to write an OpenSSL provider in Rust. I lied. So this was in C. Let's see how that would look like in Rust. For sure, it's better, right, Bob? Yeah. It has to be. So, well, the demo part you already saw. OK, so let's do provider in Rust. You see, there's OSSL provider init. You write hello world nonsense in there. You do magic unsafe things all over the place. There's a little bit of hand-waving about bindings instead of including headers from OpenSSL. And if you didn't know, this is the other Rust mascot. It's not Ferris the crab. This is Koro, the Rust urchin. Unsafe Rust urchin. So don't, it's pointy. Be careful. So we can look at, does this even work, before we discuss what is then the benefit of having OpenSSL providers in Rust. So I think I have, yes, there is the demo part. And let's see if this works. So
you really had to allow no state case just because you turned everything off.
Sorry? Yes. Yes, the Clippy is everywhere, and it's always complaining. And let's see, let's clean everything. And OK, what's happening? So running cargo to build, because cargo is perfect. And it did its magic. OpenSSL, well, a magic libello word SO file has appeared. I didn't show you what the content of source is, but there is the bindings part that I didn't want to show you because it's messy. And then there is the librs part. And the librs part is way longer than the C equivalent of the same thing, but it's exactly what was shown before. And when I run, just the last thing that was done after compiling was, OK, let's run, again, OpenSSL list with a provider called Hello World, and it's listing the providers in a verbose mode. And look, it's Rust. There's a crab, so it's Rust. And it still says Hello World, so it's demonstrated completely equivalent, but it's now a memory-safe language. And OpenSSL says, oh, providers, Hello World is there. It still tells us unable to query provider parameters for Hello World. So it's doing exactly, perfectly replication of what was doing before, nothing. OK, so, well, I think that's the end of the talk. Now you know how to write an OpenSSL provider in Rust. It just takes more lines of code. You sprinkle unsafe here and there, and handwave bindings, and it's magic. OK, so thank you for attending my TED talk. And let's enjoy the rest. And maybe we have some time before Matt has to deliver the closing comments. No. So I mentioned that QUBIP paid for me to be here, so I have to say something about QUBIP, right? So I mentioned before we have this Aurora provider, which is written in Rust. I'm not saying it's written in safe Rust. And the idea for Aurora is do not pick a winner algorithm, do not pick a winner implementation. Let's use the QUBIP methodology, shallow loadable modules, to increase the cryptographic agility. If you go at the link behind that QR code, you will see the dirty source code. Don't do it now, because you will be disappointed. But in a nutshell, when we will look at the content of the code base, basically it's a regular Rust project. There is a source folder. Inside there's a bunch of RS files. Magic happens, and then you get a provider. So what files are there? librs is the equivalent of the main function for libraries. So that's what cargo looks for when you try to build a C dynamic library crate. And in librs, a lot of, let's say, trying to abstract all the unsafety so that we can use it in a safer way is happening. But then there is this init rs file, which includes the same OSSL, well, not the same, an equivalent OSSL provider init function that actually tries to do something thanks to what is written in the librs file. We have, instead of binding RS, we have this forge RS, and I will tell you more about this later. And then we have this adapters folder and adapters RS file, which contains, in this case, 4 adapters, one for each backend that our Aurora provider supports. And each of them is providing some algorithms. Let's see this in action. Yes, there is demo time. OK, so let's see if this works. Yes. Where are we? Yes, we are at step 0. Well, we are after step 0. And step 0 means I just removed a bunch of stuff that otherwise is in the interest of being clearer, hopefully. I removed a bunch of stuff from what is in Aurora, so to show you a bare bone version of Aurora, and then we try to build up. We put back all the stuff that I removed, and then we try to see how does it look like to add one more algorithm, for example, FrodoChem, to Aurora, which was not there in the released version that you see at the link above. So if we look at the current history, basically I'm going to show you the code at this hello step 00, and let's see. In source, you see forge, helpers, initrs, and librs. There's a lot of hand waving. And if we look at initrs, you will see that in addition to OSSL provider init, that has the same name, the same kind of, let's put away the linters, and I know what I'm doing thing. And we basically are doing the same thing. We are going to be called by OpenSSL and provided a handle, a core dispatch table, a provider dispatch output pointer, and a way to store some object that is associated with our provider. And the whole thing that is going to happen in this function is that we take each of these arguments, we convert it in Rust safer abstractions. Like we have a core dispatch abstraction that does some checks before actually using it so that it is more idiomatic Rust. We create down here a new provider instance. This is the stuff that I said it's in librs and I hid it away, but that's the part where the Aurora glue is going to be useful for whatever you want to do next with this project, if you want to play with it. And then from that provider instance context, we get a provider dispatch table, and I will show you what's in there. And then you see, I say do not, we shouldn't be leaking this later. Let's ignore that. And then we return success. So very similar to what we saw in the nonsense, well, yes, in the more nonsense provider case. And then we have a couple more functions here. So we should be good citizens of the operating system and free our memory, not just leave things dangling. So OpenSSL provider core interface supports this tear down function that we can expose so that it can be called once the last reference to our provider gets evicted from memory, and then we can reclaim the memory that we created in Rust and get rid of it properly. And we also have what would be considered a bare minimum functional provider also exposes these gettable params and get params. That's the way the OpenSSL core get to ask our provider, okay, so what can you do? And let's see that in action. So, no, this is not what I wanted to do. Well, first of all, does it build? It builds, magic. And cargo hid all the dependencies away you don't want to know. We can run some tests. And will it be all green? Absolutely not. So you see that we have two failures. One is it doesn't report its expected name, and the other one listing all algorithms. The reason it's that there is no algorithms, because if you look at the details of what gettable params and get params are doing, they return an empty list of parameters. So they are just saying, you can call this function to know what I do, and then I say, I do nothing. And get params is the one that actually gets called for each params that you provide, and that's also saying success, but nothing happened. So OpenSSL gets nothing from us. If we try to use it, let's see if I can do this. Let's go with that. So there is debugging active. Actually, let me make it even more verbose. Let's try it again. OK, so there's a bunch of text happening. So it's a better hello world than it was before. So mission accomplished. Other than that, we can see that when first the OSSL provider init function was called, we do our hello world, and we call the Rust function from C. Yay, you won. It's unsafe. And it tells us which version of the provider it is. A bunch of stuff gets called. We don't really care about that. We can actually explore what is in that core dispatch table, in those core parameters that are passed onto us. We see that the OpenSSL core communicates to our provider that it is OpenSSL version 324 down here. The provider name by which OpenSSL knows our provider apparently is libaurora, and that the module file name is somewhere in a path in this container that will self-destruct after this demo is over. And then it lists the provider. We loaded the default provider as well, because all the serious decoders are there. And then it loads libaurora, which clearly is called by the core with the get params and gettable params, and we say, well, it's a stub implementation, we do nothing. And OpenSSL complains that indeed it got an empty list of gettable provider parameters, so that's why that test was failing, that tells the name of this provider is not reported as Aurora because we are not reporting any name to the OpenSSL core. And that's it, nothing else. Well, the teardown function is indeed called. We say goodbye because we are polite. And then, because we reclaim that memory, the drop magic of the safe Rust handlers happens, and we actually do free the memory, and everything is clean. And if you were to run this in Valgrind, maybe there wouldn't be leaks. OK, next step. How do we go to the next step? Go to step here. Ooh. Let's try it again. OK, just hammer until it works. So if we look at the changes here, we are up here. It means that compared to step 0, we moved 1, and I reverted the broken stubs for gettable params. What does that mean? It means that instead of the stubs for gettable params and get params, we are actually doing something. We are using the provider instance context from the void pointer that OpenSSL gives the provider every time this function is called to actually retrieve from the internal state of the provider what are the supported parameters by this provider. And then when getParams is called, instead of doing nothing like we were before, we reconvert to a safe Rust object the void pointer that we receive from the OpenSSL core, and then we actually use that context to go through all the supported parameters and the ones that are I've been asked from the OpenSSL core, and if it asks what is this provider name, we tell what the provider name is. We take it from our context. If the core asks what is our version, we report that, getting the information from our provider instance context. If we are asked what is the build info, again, we get that information from our provider instance context, and we return it in a way that is digestible by the C ABI that the OpenSSL core expects. And nothing else interesting happens. So let's see if this builds. OK, let's see if this actually fixes the tests. There is still one failure. We fixed the OpenSSL, where is it? Expected name thing, because now if we do provider list, only Aurora, and let's tune it down, the madness. If we ask again OpenSSL list providers, we actually get to list the information. So when OpenSSL core asks us, what is your name? We say, we are QUBIP Aurora demo. The version is 086 dev demo hello. And build info is whatever this means. It's like 21 commits on top of an actually meaningful provider, which shows progress. And then the teardown happens, we say goodbye because we are polite, and that's the end of this step. Let's see what is next. So now we know how, up to this point, we know how to write, how Aurora is written and how it tries to do nice idiomatic Rust things to interact with the OpenSSL core, but at the moment, this version of the Aurora QUBIP demo provider still does nothing. There are no algorithms. So let's try to fix that by actually adding one new algorithm. Yes, so I forwarded. In the history of this repository, we were here before, just fixing the stub version of gettable params. And if you look at the commits, just trust me, it's just re-adding all the things that I removed from the actual 085 version that we released of the Aurora provider. So we are adding back all the stuff. And if I actually do step 1 backward, we can do cargo test. This is with all the stuff re-added, and you can see, hopefully, once this compile and cargo finds all the dependencies. Yes, oh, this is, okay. It's still big enough. You see a bunch of green passes, that's good. And you see that there's a bunch of algorithms being tested. You see that, for example, in the PQC adapter, there's MLDSA 65 stuff and composite stuff. There is another adapter, SLHDSA-C, that has SLHDSA implementations. There was a Rust crypto one, and we missed at the very beginning the libcracks adapter showing support for X25519, MLChem 768, and other MLChem 768 hybrids. And then we do a bunch of tests. We make sure that when we are comparing with artifacts from OpenSSL or other sources, we do actually decode them correctly, we encode correctly, we can do self-signing, all this kind of fun stuff. And if we list algorithms, which was all I wanted to show. So again, OpenSSL list provider, lib Aurora to load our provider, listing all algorithms, and I will just filter out for the ones that actually say Aurora. And you will see there's a bunch of them. A lot of them are just encoders and decoders. And the idea is that using like capabilities are registered. There's a lot of stuff that I'm not going to go into now, but basically I'm showing you that it is possible to basically have as many adapters as you want, each of them supporting their own set of algorithms, and do stuff with that, and OpenSSL can see them and hopefully use them. I'm not going to demo that part with proper Aurora, but I want to progress into trying to add a new algorithm that is not supported by OpenSSL 3.2 that we are using here, and it's not even in the 3.5 because it's not standardized yet. So, checking where I am. So the only thing that I did since running the test that I just showed you, I copied the files from the libcracks adapter and I created a new folder. This is just copy-paste. If you do, of course, this is not the proper Rust way of doing it, and copy-paste is not the best way of programming, but for the purposes of this demo, it works. And let's do it with stats. Yes, so basically copying the libcracks files meant that now we have a new demo FrodoChem adapter, which is an RS file and a folder. Inside that folder, right now there is an X25519 MLChem 768 algorithm that is supported, and we can try, first of all, to see if it builds. It should. And even though the provider, the adapter is called demo FrodoChem. Right now there is nothing FrodoChem in it, and it's actually just a copy of libcracks. So it's only going to do the things that libcracks was doing before. I also hidden away the fact that I disabled, did I disable all the other ones? No, I have to go one step forward. So let's do next. Yes, the only thing that I added in this comment is basically adding in cargo toml a feature that tells, okay, enable the FrodoChem hybrid, the demo FrodoChem adapter down here, and only enable that. So now I disabled all the other adapters because I'm not interested in showing the very long passing tests that take forever. We are just going to work on the FrodoChem adapter. And nothing else really happens other than adding into the adapters.rs file knowledge of the fact that there is a new adapter called demo FrodoChem and calling its init function as needed. So if we build it now, and I think this will fail again. Or did I ignore? I think there's a test that's going to be skipped. Yes, I will tell you later offline why. But the important thing is here we can see that the demo FrodoChem adapter is exposing support for key management for X25519 MLChem 768, and it's actually running the test in it. And nothing else. Let's see. All algorithms. Okay, so among all the algorithms that this provider, that are loaded right now, there is one called X25519 MLChem 768 that is provided by libaurora. Still not interesting. Let's see what's next. Okay, so now we moved here to rename X25519 MLChem 768 to X25519 Frodo 640 AES, and nothing else changed in terms of code. So if I build and I list even though this is still performing underneath, demo effect. What happened? Sure. Oh, I just renamed the file. I didn't even change the parameters. So that's why OpenSSL still thinks, oh, this is X25519 MLChem 768. Let's go to the next step. And now in here, I updated the parameters, and we can look at it. 2 minutes. Okay, so now here is where I'm changing the parameters so that when we reply through those dispatch tables and gettable and getParams functions to requests from the OpenSSL core, we will say, oh, this adapter name is actually X25519 Frodo 640. And this is the long name, this is the description, and it says from libcraps. The security bits is under 28, and all this kind of stuff. But this is the only stuff that I changed. I just changed identifiers and numbers around. The important thing here, I needed a code point for when I am actually saying OpenSSL, we can do key exchange mechanism over TLS with this. There isn't a IETF standard or draft that has issued a IANA number for this. So I'm using the one that Open Quantum Safe is currently using as a testing code point for FrodoChem. 1 more minute. We are almost there. Yes, and you can see now it's save point, so that means it's the end of the demo. And what I did, I actually replaced the libcrax implementation of X25519 with calls to FrodoChem implementing functions coming from the FrodoChem RS file we can create. We can look at this. I mean, I added a new dependency, so now we added one more thing for cargo to download from the internet and just blindly trust. I'm saying, oh yes, ephemeral FrodoChem 640 AES, that's the PQ algorithm that in this file we are going to use. And names of object change, but you can see a public key is made out of this is a hybrid one, so there is a elliptic curve share, a post-quantum share, and now instead of being a libcrax MLChem 768 public key, it's now a FrodoChem RS encryption key object. Same for the private key. And actually now, because the sizes are different, well, the public key length for the PQ part, it's 9 times as much. And X25519 MLChem 768 is weird because even though the name says X25519 first and MLChem later, we actually encode it the other way, but all the other ones are following the same order that is in the name. So we need to do first elliptic curve portion and then post-quantum for the encoding. And it's all this. So this happens when we have to encode the share secret, when we have to encode public keys, all this kind of stuff. Like the details are not particularly relevant. But the idea is that what I want to show you, it's relatively easy to just, okay, copy-paste an existing adapter, just change the few things in the key management file that actually plug in the external implementation. And if we build, and it works, almost there. Okay, so build works. Let's see the tests. There's going still to be the skipped test while it happens. The skipped test is the one about all at least one adapter being there, and it's being one algorithm being there, and it's skipped because I wrote the wrong regex to actually filter for that. So it only looks for decoders and encoders, and this being an ephemeral chem, there is no encoders and decoders involved. So it was just failing, even though an algorithm is there. But that's on me, because I cannot write regex that actually work as intended. OK, so it's being tested. We have a loopback test, very interesting. And let's ask OpenSSL to list the algorithms. X25519 for Rodos, X40AS is there. Can we test this? Let's see. Let's see if this is the right incantation. Yes. So if you visit https://test.openquantumsafe.org, you will notice that the cool people at OpenQuantumSafe are maintaining a very interesting web server. Actually, can we go there? Well, no, we don't have the time. But go to that URL, and you will see there is a page with a big table that basically has every possible combination of, do you want this chem algorithm? Do you want this hybrid chem algorithm? Do you want this parameter set, that parameter set? Do you want to use this algorithm for signature for authentication, or this one? Or maybe you don't care. Like, there's a gazillion numbers, and it happens to be that at port 6024, there is one instance that doesn't really care about what authentication signature algorithm are you using, but it only accepts connections that implement Frodo 640AS in combination with X25519. So if the implementation of FrodoChem that we picked is actually implementing the ephemeral FrodoChem that was in the NIST round 3 that the OQS people are serving at this page, and I didn't mess up, we should see a successful TLS 1.3 connection, because we are asking TLS 1.3 connection. I'm only specifying on the client side that I support X25519 Frodo 640AS, and I'm connecting at that page. So will it work? Yes, it works. Just trust me. No, we can actually check what happened, and of course this is an unknown algorithm, but you can look at the details later. We didn't do a post-quantum authentication step, so this is only protecting you, if you believe in FrodoChem, against harvest now, decrypt later. But our implementation has been engaged, our certificate was served, all the TLS messages were super good, and we agreed on the same shared secret, which means that, at least in theory, our backends are agreeing on what does it mean to do X25519 Frodo 640AS. And that is the last part of the demo, and this is Q&A, and we have only 5 minutes left, right?
Good job for a hiccup-free live demo.
I'm impressed myself.
I just wonder what's next. If I get it correctly, it's not supposed to be production ready, or is it? Or is there, like, the project ends this year, next year, something like that? So what are your plans?
So the project ends at the end of next August. So we only have 1 year, well, less than 1 year left. There's definitely, if you go at the URL, you will see a big, bold statement that says, don't use us. But we actually mean it, not like the boring SSL people that say it, but everyone uses it anyway. You shouldn't be using Aurora unless you want to use it for playing. What is left in the project? So most of the functionality that we needed is there. Like, we support SLHDSA, MLDSA, and composites, a previous version of the draft. We support hybrid chems. So from the point of view of the supported algorithms, everything is there. the things, you remember when I said, don't go now at that link, you will be disappointed if you look at the code. We have a lot of cleanup to do, and a lot of the things that we have done so far have been a lot of copy-paste, and then let's tweak this part, because we still don't know what is the best way of automating this in Rust in a way that actually doesn't make it a nightmare to maintain rather than being useful. So we do plan to do this cleanup. The plan is also to make it so that we can declaratively generate from, similar to what OQS provider does. OQS provider has this nice YAML file that says, oh, I want this algorithm, this is the code point. It does magic, and then you get a provider at the other end. We want to do the same thing, but in Rust, and in a way that is a little bit more maintainable than YAML, because YAML is nice to see when you only care about the YAML file. If you want to tweak, for this algorithm, I want to do something special, not what I do for the other ones, then funny thing happens. Yeah. And then there's the client-side part, where we are almost done as well. And this is the part where we actually integrate all these systems, and we run the PQC TLS connection, and we put users. So I mentioned our partners from Spain. There is Cyber Voluntarios. In here is going to involve repeatedly over the next year end users, like regular users that don't have any advanced technological background. We will let them know about PQC and why they would care, and we will report what Peter said, that quantum grid analysis is bollocks, but we say that after, not on the record. And then we ask them for their experiences, impressions, and we measure things and see how many things do we break over the internet because SLHDSA is so huge, or these or that, these kind of things. So that's what's next for the project in the next year.
Anyone else?
Bob, did I scare you? Oh, Dmitry.
Do I correctly understand that you have implemented some boilerplate for making the next providers to be written in Rust easier?
Yes. Oh, that was the whole point of the presentation, and I completely forgot. I always do that. Do you remember when I said, oh, this ForgeRS file, I will tell you about it later? Did I? No. So the whole idea is that, OK, Aurora is particularly geared towards PQC algorithms. So basically, we picked the NIST PQC API as the baseline compatibility layer that every signature or CAM algorithm that has been proposed, even those that are not being put forward by NIST anymore, but that found a new house in ISO or other standard-defining organizations, like Frodocam, for example. All of them will implement that. But to make these actually useful, we created this OpenSSL provider, Forge. You will find all the links when you open the Aurora repository. And this is a separate crate that is supposed to be all the hand-waving when I say, oh, the bindings, yeah, all of that is happening in OpenSSL provider Forge. And the idea is that we do that once, we make it flexible, and you can access the various things that are hidden underneath, and you can reuse these to create your own version of a providers in Rust, so without necessarily reusing the abstractions of Aurora.
The question is, if I use this Forge, would you call it production ready? If the implementation of the algorithm was production ready, and I use this Forge, is it?
No, even Forge has a big, bold statement that says, don't use us. So part of the cleanup process that we have to do in Aurora is actually moving stuff that for expedite development we did in Aurora to take them, make them properly abstract and clean, and move them to the OpenSSL provider Forge so that it doesn't depend on specific things abstractions that we defined in Aurora, but only basic abstractions. And at that point, you should be able to really build a provider, and it's easier to inspect the Rust unsafe to safe translations. So it should make it easier for you to audit. Okay, I do trust these abstractions. Now I don't have to care anymore about doing my own unsafe transformations between pointers.
So we are running out of time. So
Okay.
yeah,
But I can take any other question offline. I'm going to be here.
maybe the last one for Mr. Bob. You want to say something there? Shortly.
Since you can, of course, still use it in production, and you have a mix and match of being able to pick wonderful new algorithms in TLS 1.3 that are, of course, not officially approved, do you have a nice also module written in Rust that can fingerprint the client and tell that when you're coming from Qualys or SSL Labs or your certification people, you only advertise the boring algorithms that, you know, the certification people want to see, and you can have all the other glorious stuff available for everybody else?
I can say, no, we don't, because I never thought about it. But let's talk about it later and see what we can do about that and trick all kind of validations.